somewhere. All right. So this early morning panel, we're going to spend talking about some a little bit more cheery compared to the last presentation, and a bit more technical. So the title is Coordinating Combining Data Processing Movements and Storage. The short word for it is orchestration. And the nice thing about it, also the complicated thing about it, is that it's sort of in the eye of the beholder. Every major facility does it in some way. They all do it differently because it all depends on their science requirements and their infrastructure, their sensors, their systems, and everything. So today we assembled a great panel that I'll introduce shortly to talk about it. Just to set a little bit of expectations and just level set the discussion. Of course, in the CI compass, there's a definition of a major facility data lifecycle. Many of you have seen this picture before. Just kind of mapping onto it. The orchestration, or the longer title of this panel, maps on all of these steps, right? And the question is essentially, how does this pipeline work? That's really what the question is about. So we tried to, we invited a collection of experts from different major facilities. And as I said, this question is very much context specific to the facility, specific to the instrument, specific to the workflow, specific to their science. So we asked them to give short presentations, about 10 minutes each, and answer some subset of the following questions. Question number one, how does your facility today deal with orchestrating data movement, processing, storage, and if needed, dissemination for the benefit of its users? Number two, what enabling technologies you see that will make this job easier in the near future? Number three, kind of a longer term question, are there paradigm shifting changes you see coming on the horizon for your users and how they handle their data movement, processing, and storage? And number four, what challenges you see going forward for them and for your facility? And so the experts we collected today for the panel are Chris Romsos from RCRV, Oregon State, Benedikt Riedel from IceCube, Julio Ibarra from FIU, and he works with a number of international network providers. And oh, this is an older version. I apologize, we've corrected it. So we had David Manson from EarthScope. He was not able to leave Denver due to weather. We're grateful to him for trying many times, apparently. Instead, we have Rob Casey representing EarthScope. So all of them, as I said, will give presentations, and then we'll open the floor to questions from you all. So please, and there will be a prize. No, there will not be, but please listen and have your questions ready. So why don't we start in just this order? Rob, maybe we'll start with you. Is that okay? Sure.
Okay. Yeah. Thanks everyone for allowing me to speak on Dave Menson's behalf. He sent me the slides last night and I just kind of went through it, and I had to sort of make it so that I felt like I could speak what he was intending. So Dave and I both work for the EarthScope Consortium. And in case you don't know, we are 1 year old. We are a merger of two NSF funded major facilities, the GAGE program for geodetic data and the SAGE program for seismic data. And so we are making a combined facility that we are moving to the cloud. And so this gives you kind of a current timeline of the milestones that we've been reaching in our attempt to get to the cloud, to get to a fully operational state. So in order to address one of the questions for this particular session is to address some of the challenges in what we might term a cloud lift or a cloud migration. So some of the things that we're encountering are cost projection when you first set out to plan out your migration. And now that we're getting a lot of components in the cloud, we're starting to move into what we call FinOps, which is where we're actually monitoring the various components and how the billing for those components go, how much usage they are seeing. And then we make adjustments to our designs and our operations accordingly in order to keep the costs at a reasonable level. We're looking for sustainability. So things where we're hoping to find cost savings in terms of strategy could be contract deals that we could make in the future to bring down our operational expenses. And we're seeking ways to get agreements for open data qualification for our archive, which is in total in about the 2 petabyte range. Egress is really our major operational cost consideration. We are aligned with the commercial cloud, and as you know, because we're a data center that puts out a lot of data as part of our mission, this is our primary cost concern. Also, identity management and data usage tracking requirements that have emerged in the past few years have added some complexity to us. And it's not just a technological complexity. We're having to move the community along with us and get them trained up to embrace authentication and authorization processes to get at data. We still want to send the message that, yes, this data is open, but we would like to know who you are and give you back some benefits of us actually being able to identify you as an operational user of our services. On-premise software and systems are not as cost-effective in their current form. And so what that means is moving to the cloud is not as simple as just picking up your VMs and lifting them into the cloud. You can do that as an emergency measure, but what you're going to quickly find is those tend to be, they're a lot more static and they tend to be a lot more of an expensive option than utilizing what managed systems are available. Containerization is also a very good strategy to move towards. Attempting to avoid vendor lock-in is a very admirable mission. However, we've discovered that as we've tried to embrace going with cloud agnostic designs, that once we actually got latched onto a vendor, we started looking at what the vendor had to offer and saw an actual benefit with going with what the vendor, presented as managed services. So we kind of see it maybe as being more of a fear of change than an actual real concern. In reference to what I was saying earlier, we are doing a corporate merger. So we are actually bringing together processes and people from 2 different companies. And we've had to, this past year, make our culture as one and work together as a team and be concerned for both programs. And so it's been a very interesting adventure, both doing a technological shift as well as a cultural shift within the company. So again, our important aspect of all these changes is our messaging to the user base. And so naturally, you can imagine our geodetic and seismic communities are really concerned about seeing such change occur. It's a pretty radical shift, not just the brand naming, but all of the potential losses that they could experience in the services that they've enjoyed over the years. So we continually try to press the message that there is no plans to deprecate current capabilities, data formats. We have lots of standards that we've built concurrently over the past 3 decades. So we are not going to abandon our community in the effort to jump the chasm completely into the new. The only significant change that impacts everyone, users and staff alike, has been identity management. But we've been working with the community for the past 3 years on getting them adjusted around authentication to our systems. And we already have a number of data systems that require identity management for access. So I think we're being pretty successful in that venture. So let's address egress of data again as an expense. It's the estimate is that anything that's being exported to the internet to a client that's sitting out in a different location costs about 9 cents a gigabyte to transfer data to them. And that's a pretty small amount of data that we tend to put out every month. In fact, we currently export about 1 petabyte of data per year. So a rough estimate is about 110K per year of cost, which in many ways is actually very similar to the cost you could expect running on-prem with a mass storage system where you have to do a large overhaul every 5 years. This gives you actually a year-over-year constancy of cost. So when we look at these costs, we ask ourselves, can we try to keep those down by transitioning power users, the ones that access hundreds of terabytes, maybe for some very big experiment? Could we actually encourage them to co-locate within the same cloud region? Because that strategy means that we can actually engender little or no egress cost. So in leading to off of that logic, we could say that maybe we could train our users to do their work in AWS. So maybe an on-ramping program where we actually train the user community to become comfortable with using the cloud and actually doing their work in the cloud close to us. So we could set up programs for training to our user community. We may be able to work out programs for account subsidies, especially for those who are in need. Limiting internet download in favor of local clusters. So we could do some rate limiting in terms of egress access. And also providing notebook resources or other compute resources on our systems or co-located to those systems in AWS. So those are just a few of the possible strategies where we could actually bring all the community into the cloud with us. Also, we're still looking at open access capabilities. So if we can get some of our data to qualify for open access, it gives us some incentive because that data can be downloaded as much as possible, and we're not going to engender costs from that. But we may not be able to track its usage, and that gets back to one of the core reasons why we're moving to authentication is because we are being required to track not only how, who's using the data and what data and how much, but we also want to get an idea of for what purpose. Okay, thank you. So I'm going to, in the last 2 minutes, talk about some of the advances in data ingress that we've been building up in the cloud. So we have a unique opportunity to redesign our data flow systems, and is thematic to this session. This diagram shows you ingress processing of GNSS data coming from many remote geodetic receivers in the field. And we have some legacy systems that used traditional TCP communication, but there are also a number of facilities that transmit data to us using a RabbitMQ type of exchange. And so we are embracing Kafka and similar types of queuing systems to control the flow quickly through systems, allow branching to various other forms of flow, and do compute in near real time or real time. We can also do other types of messaging, such as configuration that works with Kafka. And so you can see now a system that uses interchange in a much less coupled fashion, where you have lots of components being able to exchange messages to each other and everything processing at its best rate. We also are ramping up, excuse me, our use of observability, because we're not able to access our systems and look at them in quite the same way as we used to with on-prem systems. We're not going to be able to log into a Lambda that's running for a brief few seconds or something like that to see how it's running. Instead, we're capturing logs through many different flows, and we're setting up dashboards that we can use to monitor many things running at the same time and get an idea of success and failure, the volumetric metrics and so forth, and we can actually use those in our reporting. This example shows how we can track the geolocation of clients that are connecting to us, and we can get that first really good look of who's accessing our data and to what level. I'd like to give mention to the Shake Alert program. EarthScope is quite involved in it, and this diagram represents the Gauge program's intimate involvement with Shake Alert, in that they are the geodetic facility feeding data in cooperation with the USGS. So the USGS receives real-time data feeds from many geodetic stations within the Shake Alert zone. And so this system you can see is also using heavily things like Kafka as for messaging and doing analysis and so forth. So we have a data flow system that has much less latency going from end to end. We're trying to achieve the requirement of being near real time to real time available in both geodetic and seismic data to the community. So this diagram shows you an example of how we can have real-time observability. And this is the sort of thing not only used by staff, but they're used by researchers and by those concerned with Shake Alert. And so we can look at many different types of metrics or measurements. That middle diagram there along the California coastline is standard deviation of peak ground displacement. And we can use heat maps to show probabilities of latencies. So it's kind of showing kind of where your general data latency is for the Shake Alert system for continuous monitoring. And so that's completes my talk.
Thank you. Please hold your questions, and we're going to go with Julio next.
Good morning, everyone. My name is Julio Ibarra, and thank you, Eva and Ilya, for the opportunity to present to you about the AmLight network and how it supports major facilities in Latin America and the Caribbean. This is the outline of my talk. I will talk about the AmLight Express and Protect network. We refer to it as AmLight EXP. The Express represents network paths that are used for express movement of data, and the Protect are protection paths, basically, for the network. I will also discuss how major facilities are being supported on AmLight EXP and present a use case that's an SLA-driven science use case involving the Vera Rubin Observatory. So first I'll talk a little bit about the AmLight Express and Protect network. So AmLight, as we call it, is an international research and education network. It was built to enable collaboration among the communities in Latin America, Africa, the Caribbean, and the United States. It's a project supported by the National Science Foundation in the International Research Network Connections Program. The award number is there. AmLight is based on many partnerships that we have with the research and education networking community in the US, Latin America, the Caribbean, and Africa. And the project has been built over many, many years of trust and openness. It's been evolving for the past 20 years. And we depend on sharing infrastructure resources among all of the partners and also human resources. The network engineering community is very rich and vibrant in supporting the network. And to the right are logos of all the different organizations and projects that are participating in AmLight. This slide shows you a representation of what the network footprint looks like. As you can see here, it spans from the US to Latin America and all the way to Africa. And we also have a connection to Europe. So the network supports 600 gigabits of upstream capacity between the United States, Latin America, the Caribbean, and 100 gigabits to Africa. We are adding more capacity in 2024. There's 400 gigabits of capacity that's going to be added between Buenos Aires and Sao Paulo to support Vera Rubin and other major facilities that are in Chile and in Brazil. We also will be adding 200 gigabits of capacity between Sao Paulo and Boca Raton, Florida. That will be part of an express path as well for Vera Rubin and other facilities in Chile. We operate open exchange points, 3 in Florida. There's 2 in Brazil. There's 1 in Chile, Puerto Rico, Panama, and South Africa. We've opened up a new exchange point in Atlanta, Georgia, and we also will be opening up 1 in Buenos Aires, Argentina. AmLight has been running as a production SDN infrastructure since 2014. So we are able to do deep programmability on the network because of it being software defined. And we have programmability across the network stack. Our data plane is fully programmable with P4 switches. We have an open source SDN controller that we own and continuously develop and improve. We have fine-grained telemetry provided by the data plane with the P4 switches, and we use that telemetry to be able to do runtime network verification to verify that the network paths that have been provisioned are the ones that are being used. And we also use closed loop orchestration we have different types of instruments on the network, such as Personar, S-Flow, telemetry devices from Juniper, and also in-band network telemetry that allows us to do real-time telemetry. I want to give you an example of how we closed-loop orchestration. This is a very busy network stack that you see here that represents the architecture of the SDN infrastructure. So the workflow starts actually at the data plane. From the network, we use that telemetry report and export it to the management plane. I'm missing some colors here, so it's a little bit confusing. But then from the management plane, computations are performed on the counters as well as the telemetry reports, and that computation then allows us to identify the network state. The network state is then exported to the intelligence plane, which is where we do interpretation of the network state using a component that we are developing called the Behavior Anomaly and Performance Manager, or BAPM. Notifications result from the interpretation of the network state by the intelligence plane, as you see here going on the right-hand side of the figure. And these notifications and traffic engineering policy goals trigger intents to modify the behavior of the network, and that is then moved to the control plane on the left here. And what you're seeing here that represents the closed loop orchestration are the arrows in red. So this is continuously running, okay, with the different exports that we do across the network stack. And it runs as autonomously as possible. Notifications are sent to a network management system, and it's always an option for a network operator to intervene if necessary. But the idea is to be able to do this operation as autonomously as possible. We use the data from the telemetry to do network verification, as well as packet provenance, so we know where every packet has been and how long it's been there. And through the instrumentation, and we're able to, and the closed loop orchestration, we're able to reduce the need for operator intervention as much as possible. So some of the major facilities that are supported on AmLight are shown here. We have NORLab connected in Chile. ALMA is connected in Chile as well. Vera Rubin is under construction in Chile. We have the VLA. There's an antenna in St. Croix. Fabric is also a facility that is connected to AmLight. The Wall of Wind at the Florida International University campus. And we also have connection to Open Science Grid and PATH on AmLight. So this diagram gives you a representation of how the network is interconnected with all of our different partners. So the major facilities are supported in Chile, Brazil, the Virgin Islands, Florida, and Georgia. The blue clouds show you where the major facilities are connected. The purple clouds represent different networks that are participating in AmLight and that we connect as well through this topology here. You could see all the different types of paths that we have and the different colors. The green represents the express paths. that are currently moving data and supporting major facilities. The red represents the protect path, and then the darker colored segments are shared paths that we have with our network partners across the network, providing a lot of resiliency and for high availability of the network. The open exchange points are also very critical cyber infrastructure in the network. They're represented here by the ellipses that you see connecting all these different green segments. And they provide flexibility to be able to place computation and storage closer to the major facilities as well. So this is, I think, a very key point of an infrastructure like this to be able to support major facilities in the service area that we have involving Latin America and Africa and the Caribbean. So I'd like to present an SLA-driven science use case with the Vera Rubin Observatory. So as most of you know, the Vera Rubin Observatory is an instrument that has significant demands on the network performance. It is under construction. It's a large aperture, wide field, ground-based optical telescope. It's currently under construction in northern Chile. The telescope will take a picture of the southern sky every 27 seconds and produce a 13 gigabyte data set. Each data set must be transferred from, is to be transferred to the US data facility at SLAC. This is a transfer from northern Chile all the way to SLAC at Menlo Park, California. And this has to be done within 5 seconds inside the 27-second transfer window. So essentially the network has 5 seconds to move a 13 gigabyte data set from northern Chile all the way to SLAC. And if we miss that 5-second transfer window, then there is a miss in terms of the overall movement of the data image. And it impacts the cadence of the observation, because this is a survey telescope. So every 27 seconds, it's taking a picture of the southern sky. And so this is a very challenging use case for the network. There's high propagation delay in the end-to-end path. The round trip time from the base station to the USDF is approximately 180 plus milliseconds. And we've calculated that if there's 0.001% of packet loss, it will compromise the Rubin Observatory application. So the network has essentially, using the programmability capabilities that come with the SDN infrastructure and the programmable data plane and the telemetry, we built the closed loop orchestration to be able to allow the AmLight infrastructure to continuously monitor the network and reprogram the forwarding plane in response to the SLA requirements. Now, for observation like this, it's really critical to have the autonomous operation working, because they operate at night. So if there's a failure like at 3 o'clock in the morning, a network engineer is not going to be able to respond to the requirements of the SLA. So we have to have autonomous operation to do this. And so this is something that I think major facilities should start to take advantage of in an infrastructure like AmLight and other research and education networks that are using telemetry as well. So to close, I'd like to just comment that AmLight supports SLA-driven science applications, as well as use cases that have specific requirements and demands of the network infrastructure. You've seen in the diagrams that I showed in these slides that AmLight has many different paths for express movement of data, as well as for protection. We have at least 28 possible different paths to go from northern Chile and from all the way to Atlanta. And we also have a connection all the way to South Africa as well. The network supports the SLA-driven application requirements. We're able to respond to any kind of network events that occur as a result of the telemetry and the closed loop orchestration. And we're trying to build the networks to be able to run as autonomously as possible. So that way, major facilities are able to take advantage of this and be able to depend on a network that offers resiliency and can meet the requirements of your science applications. So with that, I'll end. Thank you.
Morning. Hi. Well, thank you, CI Compass, for inviting me today. This is very exciting. I'm Chris Romsos. I'm the Data Presence Systems Engineer for the Regional Class Research Vessel Project. You can giggle. It's a little silly title. I have a good sense of humor. I work at Oregon State University, and I'm here today. So I told you I worked for the Regional Class Research Vessel Project. That's a MREFC construction project. We're delivering our ships into the academic research fleet. So I'm really going to kind of step out of that box and probably talk a little bit more about the fleet. But my perspective comes as a facility user. I worked in paleoseismology, active tectonics for a dozen or so years. And you see in the picture here, that's a picture of our first vessel. We're going to build 3. And the second picture below it is that's my first research cruise as a chief scientist, and it's basically as fast as you can drive a boat for 29 days to collect data. That's about what you can cover. So let me give you a little bit of background about the academic research fleet. I really feel like we're kind of a unique facility. We're very distributed. We're a true distributed facility. We have 17, currently we have 17 vessels operating in the US, and they're run by 10 different operating institutions, right? No 2 vessels are identical, quote, identical. I think a number of them were built as kind of carbon copies, but when you deliver them to an operating institution, lots of the decisions, they drift, the configurations drift. We are building our RCRVs as basically exactly the same, and intend to manage them with a high degree of configuration control to the best of our ability. But they are very unique facilities, and there are some unique challenges to working on a research vessel and moving data. So basically your edge processing, but it's all the people that you bring on the boat. Communications from the ship to shore are problematic and slow, but that is changing rapidly. So if you were to ask our community what the biggest challenge that they have is, they'll still tell you bandwidth, but the walls are, the landscape's changing with Starlink. Communications are getting much better. We're getting redundant systems on the boat. We're shooting for 5 nines uptime. So what happens next when you get that bandwidth? And that's kind of what I'm focusing on in my project. The other thing I want to mention about the fleet is we really function as a true laboratory system. You come, you do your research on the boat. You don't exchange much with shore, with your partners, with your social networks, with your support networks, because of those bandwidth limitations. And you usually walk away from the vessel with a nice data distribution that they give you on a hard drive. But I feel like we're moving to becoming an observing system. Our vessels are being outfitted with really robust suites of equipment that we're starting to operate continuously. So let me talk about that for a minute. All the vessels have this suite of instrumentation. We call it the underway data. And you may or may not be run continuously, but anything that's collected in those resident systems on the vessel makes its way to an assembly center that we call rolling deck to repository, or R2R. This was a homegrown effort in the community because the operators of the vessels kind of realized, well, it was their responsibility to get that data. So 10 different organizations, 10 different ways to get your data to the repository. R2R was conceived as a way to kind of throw a rope around that and assist. So they're they don't mandate anything, they suggest, and they really service their customers well, and they make sure that within the time frame of about a year, the data that the vessel collects from its underway equipment will get to the archive, which is, I think, principally NCEI. We collect meteorologic data, so everything from winds, pressure gradients, things like that. We continuously pump seawater through our vessels and sample that surface seawater. We have profiling equipment. We have a lot of acoustic equipment for remotely sensing the seabed and the biology that lives in the water. So from that suite of underway equipment that the vessel might have, there are really only 3, maybe I could have included a 4th type of data stream or data type that has any type of formal kind of continuous obs. And probably the best example is our met and atmospheric systems. We send 1-minute binned data in a email package to a group at Florida State called SAMOS. So every day SAMOS gets an email that's kind of it's a summarized or it's a reduced data set. Most of our equipment samples at about 1 hertz, so reduced by 60 times. And that partnership with SAMOS, what they will do is they provide open access to the MET community, the forecast community, and they'll have some of their own research objectives. But the value that they add for us is they're feeding back what's going on, because our technicians on the boat have to make sure scientists deploy equipment over the side safely. They wear a lot of hats, and they're not CI professionals, but they're very technically competent. So that partnership with SAMOS gives them a quality control. And there's a strong trust, and so that's a kind of our best example. Another example is with our acoustic Doppler current profiler. So a profile, a vertical profile of how the currents are moving underneath the ship. There's a group at University of Hawaii that developed a data acquisition system for that particular kind of equipment and partnered with the fleet to monitor. They get an email once a day also with summary graphics and statistics about how the equipment's operating, not the actual data. It's much too large to send over the satellite. And then the third one, we have a pooled equipment. We operate gravimeters on the larger ships. And so there's a group at Hui that helps provision that equipment and really doesn't do a lot with the data management side of things. So that's not a very long list. I think there's one that I left off that we're starting to see in the fleet is atmospheric sampling equipment. NOAA is helping us equip our vessels with systems that can monitor CO2, methane, things like that, and help us pay for, get good pricing on things like standard gases and stuff like that. And there's data agreements, but that's not very widespread in the fleet yet. So not a high degree of not a lot of data moves off the ship to communities on the shore yet. And then outside of that umbrella of underway data, there's all the data that the PI might generate on the vessel. And that's pretty much the responsibility of the PI. It may make it into our cruise distribution if the PI decides to use our storage. Then we have access to their data and we can help them get it. But that's rare. Most PIs bring their equipment with them. Most recently, we had a PI who had a 40 CPU, 1 GPU Western Digital device and a video plankton recorder that would send video up a fiber optic cable, and they were able to do segmentation on the video and some inference while they were at sea to identify what organisms in the video, to make sure that the data that they were collecting was of good quality. So, and that's just kind of the tip of the iceberg. And they had to bring that infrastructure on board, and we generally couldn't support that volume of data on our resident systems. About 2 minutes. Okay, I will go a little bit more quickly. So what's changing or what's the enabling technology? I think at the top of the talk, I said that everybody will tell you it's bandwidth, but bandwidth without a plan, will just be consumed by services to make, run your life. And while you're at sea, you need to do all the things you do at your normal office. So as part of the build for the RCRV project, and kind of goes to my title as data presence system engineer, was to kind of take another cut at telepresence, which brought you visually to the boat where you can interact with, say, a submersible. But we were still leaving quantitative information. We were sending video, but we weren't sending raw data. So my problem space was, what can I build for our scientists that allow them to reach out to the people on shore that aren't on the boat, but that can help them, because you might be sick. You might have been up all night to make sure the equipment actually got off the ship and back onto the ship, and you haven't actually been able to reduce it to information yet. So the data, transport it over the network to a central data logger, but on the ship, and provide us a number of web services. There's the GIS backend, a couple different APIs. We're heavily invested in ERDAP, but we publish each sensor as an MQTT publication and send that home to basically an identical system on shore that gives the shoreside user the same visual experience, all the same data set. And I think if we would have stopped there, it wouldn't have succeeded. We spent a lot of effort focusing on our techs that are on the boat and how they interact with the system. And we learned that if it was going to succeed, they needed to want it. And so we built a lot of management capability. So now you can have technicians on the shore that can pre-configure equipment for you, build all the metadata, and maybe if the tech wakes up for their shift, they can install it, get it working, and not have to worry about all the stuff that they would have done at the end of the cruise, kind of incomplete. So I'll end there. If you didn't take any questions during the panel, thank you very much.
So hi, I'm Benedikt. I'm the computing director for IceCube, and just a sort of quick overview of what we do in IceCube data management. So as many of you all know by now, IceCube is at the South Pole, and we of course don't have a direct link to anybody necessarily. So what we have to do is basically we have three different paths for our data, where we have something called the alert data, which is mostly used for our multi-messenger astrophysics data, and then of course sort of continuous monitoring of the detector. So we do have people on station year round, but they're not experts at everything. So to have some connection to the experts in the north, we have an Iridium system. So it's, that also works as a modem. So basically just a classic old telephone modem. Then we have something called TDRS, which is provided by NASA, which is about 100 gigabytes a day, or to about 400 gigabytes a day, which is a reduced data set for IceCube that we all shuffle every day or once a day, maybe a little bit delayed. And then ultimately we also have a raw data stream, which literally is disks being written to at the South Pole, and then shipped via plane and ship, and then again, sort of planes, trains, and automobiles, also to UW-Madison. And then from there, we distribute our data out to the community, and the community being IceCube, but then also our friends in the multi-messenger astrophysics communities with LSST turning, or Vera Rubin turning on, and LIGO. Those are sort of our big partners there. So on the other hand, now we're in the northern hemisphere, or we're in Madison at this point. So we do have a global heterogeneous resource pool, so we're very much invested in things like Open Science Grid and PATH, and we mostly have shared and opportunistic resources. So we don't own a lot of our resources that we use. There's also not a lot of data reuse. We have a very large data set and a very active community that has a very broad science reach. So a given data set is being analyzed in multiple different ways. And that really, in the last 12 years of operation, basically, we've noticed that, data is being reused, but not at a rate that really is sort of good for caching. We host most of the data centrally for access to our researchers at UW-Madison. But then also what brings that back is that all the input and output data needs to be moved back and forth from into UW-Madison. So we've become very good friends of our campus research network team to basically facilitate that. And ultimately, we also have archival, which the raw data is at NERSC, which is done through Grid FTP, and then the process data is moving to Daisy Zeuthen in Europe, also through Grid FTP, but we're changing all of this to HTTP in the next coming months. So what enabling technologies we have right now? So the big one is HTTP-based transfers, where we're deprecating our Grid FTP. Ultimately, the token-based authentication, we're hoping that this will give us more management of our own data access for people, rather than having to rely on X509 certificates and how they're issued and who issues them and things like that, and when they expire. Rather, we are in charge of basically authentication authorization at this point. And then the big other thing is column-based data formats. As our researchers move more and more into the AI world, column-based data formats are really something that they are looking at, because they're really just looking for a certain data product out of our entire data set, and they want to export that entire column into their AI training or into their AI inference at this point. So the paradigm shifts are really AI focused at this point. So on the training side, again, there's this cost benefit analysis that I talked about yesterday in my other talk, which is, the purchase of ML training hardware is at this point is very hard to justify, just because it's a large investment in a relatively large investment on the order of $500,000, depending on what you're actually buying. So, and given that you only have a small group of researchers that might be working on this right now, it's hard to justify such a purchase for, one or two projects at this point. So we need to outsource a lot of this to HPC centers, which means we have to move a lot of the data from our local storage into the HPC center to effectively train our models. Similarly, AI inference and sort of the speed up it gives us in our data analysis there, sort of the streaming data versus data pipeline, and also questions about offloading this to a third party. So this is something that we call inference as a service. Basically, we set up a service and people talk to it over HTTP. This is something that the folks at CMS and LIGO are also doing. So we're kind of taking that idea and applying it for IceCube as well. But this is a very big paradigm shift, because we're moving towards this as a service model in terms of data. Similarly, distributed file systems are also evolving. We traditionally have used distributed file systems, so Lustre or GPFS or whatever you want to call, or whatever you use in that space. And now object stores are becoming a lot more popular, and they are giving us sort of distributed, they're giving us advantages in the form of, access management and also sort of resilience in some respects. But then at the same time, teaching researchers about this requires file cataloging, metadata, and things like this. This is sort of something that I've been very much thinking about in terms of metadata handling and file cataloging, or in this case, event cataloging. So, and something else is event-based processing. So this is kind of grows somewhat specific to IceCube or other particle physics experiments, or even LIGO, is that we have something called events, or sort of very well-defined periods of time or of data that we could process on. This is sort of the smallest unit of processing for us. And how do we get to that level? That rather than having to deal with files, we move to sort of a much more granular level of view of our data to improve our processing, but also to really get more efficiency out of that. And then the paradigm shift really is the sort of the IceCube upgrade. So we're on a path to a new, or to improve our facility. That means the big goal here is better calibration of the detector, which means the whole, at that point, 14-year data set will have to be reprocessed. So this is sort of trawling through 7 petabytes of data and redoing that most likely multiple times, just because we have learned over the last 12 years that we will make incremental small changes to our calibration that have very significant impact on our science. So with this better calibration, we ultimately see, at least 2 to 3 of these reprocessing campaigns coming ahead. And that's really something that is a shift for us. We've only done this once so far, so now we're going to be in the business of doing this repeatedly. The challenges is really ultimately funding. We have to do more with less. There's a little bit of scope creep. We've heard a lot about FAIR and open data, but at the same time, we have an ever-increasing data set. It grows linearly. We know how much it will grow. I mean, there will be a little bit of a change in our trajectory with the upgrade, but ultimately, our funding stays constant and our data set grows. So how do you sort of marry the two in that respect? And the other question is how much AI? If you talk to folks about AI accelerators, you will hear a lot about how they are enormous at consuming data. 400 gigabits of networking can easily be absorbed by these accelerators. And how do you feed that much data into the accelerator either from our file systems, or how do you move that data to that accelerator is really a big question. The other big thing is this shift to more external resource providers, as we can't justify, or I would say question about what our students doing or researchers doing. We need to shift towards more external resource providers to really operate efficiently and effectively. There's, of course, shift in technologies. NVIDIA will come up with something, Intel will come up with something, AMD will come up with something. And then that really shifts our technologies and and what exactly we buy, since we sort of operate on this yearly cycle. But then, students want to be at the cutting edge. And ultimately, we can't buy another the A100 box, the H100 box every year. But even getting them at this point is difficult. And then ultimately also archival. This is something that we talked about yesterday in the breakout session. There's sort of this ominous, how long are we going to keep the data around for? How are we going to do this? For example, we currently use NERSC, but I got an email yesterday that our allocation got canceled. So I talked to Dan. He'll take care of it. But ultimately, I mean, this is a 6-month project I just got handed. And this is because we rely on third parties at this point, and that's difficult. I mean, I now have 6.5 FTE has disappeared from my group basically for 6 months. So yeah, that's it from my side.
Thank you.